started. So in the last class, let me recap what we discussed in the last week lecture. We have got only one lecture on Friday. So in that lecture, we discussed about conservation of mass, in which we derived about we discussed the continuity equation. So if you remember from previous week that we discussed the conservation of mass, and then one of the major significance of continuity equation is that we can define stream functions for steady incompressible two-dimensional flow. So stream function is defined in terms of velocity by the given relations. Here, psi is the stream function which is equal to u is equal to partial psi upon partial y, and v is equal to minus partial psi upon partial x. So what is the advantage of deriving the stream function? That is that because in the original two-dimensional flow we have got two dependent variables, one is u and one is v velocity. So we can replace it with one stream function. So and we can see that if we put the value of u in terms of stream function in the continuity equation, we can see that stream function does satisfy the continuity equation. And then second thing we discussed that this stream function, if we have got constant value of stream function along a line, so that line is called streamline. So how do we do that? That we know that for the stream line, the slope of the line is v upon u, and if we try to get the slope of a line on which stream function change is equal to 0, that also comes out to be v upon u. So it means that a line on along which the stream function value is constant, that is the line, that is streamline. And we all know that streamlines are used for the visualization of flow field. An example of that is a flow around an object here. So we can easily see that the flow will diverge due to the presence of this object, and there would be a stagnation point somewhere in the front of the body, and then wake region at the back, which we are going to discuss later in this course. So at the moment we would focus just only on the streamline and stream function. So then we discussed that change in stream function across a streamline, that is related with the volumetric flow rate, and dq is equal to d psi. So we discussed this thing on the whiteboard as well in the last class. So that was the last slide which we discussed last week on Friday. So if you have got any query, you can ask. Otherwise, we can continue with some of the numerical problems for the stream function and then move on to next topic. So no queries. That's good.
Sir?
Yes.
सर ये साई फंक्शन अक्रॉस चेंज हो तो ये वॉल्यूमेट्रिक इक्वल होगा या
जी हसन
along
okay Hassan, if I repeat that along a streamline, that psi function, which is stream function, that does not change, right? So it can only change across the streamline, and flow always happen in between two streamlines. Do you understand, Hassan?
Yes sir, clear होगा.
Okay, thank you for asking. Okay, so let me continue with a few numerical problems related with stream function. So that was the last slide which we discussed, that the stream function in the polar cylindrical coordinates, and we will see its application in the coming numericals. So the first numerical problem we are going to do is that for each of the following stream functions with stream function unit r meter square per second, determine the magnitude and the angle of the velocity vectors makes with the x-axis at x is equal to 1 meter and y is equal to 2 meter. So we need to determine the magnitude and velocity angle of the velocity vector at these point. Point is given x is equal to 1 meter and y is equal to 2 meter. So first of all, the first one is psi is equal to xy. So let's do this problem on the whiteboard. So now we have been given psi value that is equal to xy. Now, first of all, we need to calculate u velocity and v velocity, because we know that if we want to calculate velocity magnitude, that is equal to, if we are talking about two-dimensional flow field, which is the case here. So v would be equal to u square plus v square, and if we want to get the angle with x-axis, so that would be equal to tan inverse of v upon u. And v is the here. Let me write it. This is v. So let's put. So v is a vector which can be written in terms of x velocity component and y velocity component. Ui plus vj. So yes. Any question? There who has unmuted the mic. Usama Aslam, have you got any query? Okay. Please keep your mics mute if you have got nothing to contribute, and once you have got any query, you can unmute your mic. Okay. So first of all, we need to calculate u and v velocity components. So as we discussed in the last lecture, that u is equal to partial psi upon partial y. So if we take y derivative, so u would be equal to x, and similarly, if we want to calculate v component, that would be minus partial psi upon partial x. So that would come out to be minus y, right? So we have got these two values of velocity. Now, what can we do? That here we can get the value of x and y, and we need to determine the u and v velocity at x is equal to 1 meter and y is equal to 2 meters. So if we calculate that, so u would be equal to 1 meter per second, and v would be equal to minus 2 meter per second, right? So now we have got this. So after that, we can calculate velocity magnitude. So velocity would be equal to u square plus v square. So it would be equal to 1 plus 4, and that would be, its value would be equal to 2.24 meter per second. Similarly, we can find angle which is tan inverse of v upon u, and v is the y velocity component, u is the x velocity component. So from here, tan inverse of minus 2 upon 1. So that comes out to be minus 63.4 degrees. So if I draw that on, you must know that how to draw it, because here if we have got x-axis like this, so it means that this is kind of minus 2, and if we take it like this, so that is the minus 63.4. This theta is equal to, this is v velocity component, this is u velocity component, this is that 0 0, and then this is v velocity vector. So u and v minus 2 and this is 1. So we can see that theta is equal to minus 66.4 degrees. Now similarly, the second stream function, which is minus 2x squared plus y. So now the psi is equal to minus 2x squared, I think minus 2x squared plus y. Okay. So for this, if we calculate u velocity, that would be equal to minus, that would be equal to partial psi upon partial y. So that would be equal to 1 meter per second. And then because this first term would be 0, then v velocity component would be equal to minus partial psi upon partial x, and that would be equal to minus 4x. Now we need to calculate the velocity vector
Sir, plus 4x.
Okay, yes, you are right. Because it is minus, so it should be plus. That's absolutely fine. Thank you for the correction. Because if you see here it is minus. So because it is minus, so it means that now minus into minus would make it plus. So now u and v velocity components are written in terms of x and y. U is a constant value, v depends upon x. So now the points where we need to find that velocity, that is x is equal to 1 meter and y is equal to 2 meters. So if we look here, that u velocity would be constant for the flow field because it is the constant value of 1 meter per second. But the v velocity would be equal to 4 into, let me see it again, x is equal to 1 meter. So v would be equal to 4 into 1, and that would be equal to 4 meter per second. So then again we can have v velocity magnitude. V velocity magnitude would be equal to 1 square plus 4 square. So it would be 17 under root, and that would be equal to, the value would be equal to 4.12 meter per second. Now the second thing we need to do is that to calculate the angle. So that would be equal to theta would be equal to minus not minus tan inverse of v upon u. So v velocity, we know that tan inverse of 4. So tan inverse of 4, if we do that, and that is equal to, theta would be equal to 76 degree to be exact. So it means that if we draw it here, velocity vector, so because it is positive angle, so it would be something like this. If this is a u velocity component, this is v velocity component. So this is 1 meter per second, this is 4 meter per second. So here we can say that we have got, this is the velocity component v. Then this angle is theta is equal to 76 degrees. Right. So now we have got, okay. It should be something. Okay, so we have done this, but there is another thing we need to find here. If you look at the end, they have written, the question statement say that locate any stagnation points in the flow field. Okay, from your FM1 knowledge, what is the stagnation point? Hassan, anyone? What is the stagnation point?
सर आई थिंक स्टैग्नेशन पॉइंट वो जहाँ पर वेलोसिटी वेक्टर 0 हो जाता है.
बिल्कुल ठीक बात है. Excellent. I think it is still Hassan. So thank you for your Contribution, yes, indeed. That stagnation point is the location where we have got zero velocity. So if we look at the now, if we look at the first stream function, which was xy, so if we see the velocity components in that first part, when we did the derivation, so here, if you look that u is equal to x and v is equal to minus y. So is there any point at which if we can get zero velocity? Is there any possibility, any value of x and y which can give us zero value for the velocity vector? So I think that would be, if we say that x is equal to 0 and y is equal to 0, it means that at the origin of this, from where this velocity flow field is there, there would be a point where x would be 0 and y is equal to 0. So that is the point where we have got a stagnation point. So I hope that you understand this point, because the stagnation point is the point, I repeat, where the velocity vector is equal to 0. So velocity vector would be equal to 0 when x is equal to 0 and y is equal to 0. Now let's move on to the second stream function, which was equal to minus 2x squared plus y. Now if you look the calculation of u and v, that you can readily see that u is a constant value, which is 1 meter per second at each location of the flow field. V velocity can be 0 at x is equal to 0, because 4x would become equal to 0 when x value is 0. But u velocity component cannot be 0, because it is a constant value, which is 1. So it means that for the second stream function, which is minus 2x squared plus y, there is no stagnation point. So I hope that it is clear. If you've got any query, you can ask. Okay, now the second numerical which we are going to do, that is the radial velocity component in an incompressible two-dimensional flow field, in which the x or z direction velocity component is equal to 0. So V of r is equal to 2r plus 3r square into sine theta. Determine the corresponding tangential velocity component, which is v theta, required to satisfy conservation of mass. So it means that because the velocity vectors are given in cylindrical polar coordinates, so we need to write to see the continuity equation first of all, which we derived in last week here. I think so. For the steady flow field, we have got this relation, in which we have got steady and compressible, and for the steady and incompressible, the continuity equation is given by the last relation. So let's do that. First of all, we put that on the whiteboard. So let's first of all we copy it. So this is the velocity vector. No, I think this is the continuity equation, and now we need to see that velocity component in the numerical problem. Okay, that's fine, I think. So now if we go in the statement of the problem, fine. So now V of r is given 2r plus 3r square sin theta. So we write it there. V of r is equal to let me 2r square 2r plus 3 2r plus 3r square sin theta. And the second thing we have been given v of z, that is the velocity in the z direction, that is equal to 0. So we need to determine this v theta value, which is shown here. So if I write this equation, the continuity equation, 1 upon r partial r v of r divided by partial of r plus partial v theta upon partial theta. 1 upon r I have taken common, so I know that 1 upon r cannot be 0 because r is a finite value. So if it is infinite value, only then this equation would be 0 due to this term which is 1 upon r. But we know that r is a variable, so it is always non-zero, 1 upon r. So it means that we can say that partial of r v of r divided by partial of r plus partial v of theta upon partial theta is equal to 0. Now v of r is given. So if we want to calculate v of theta from here, it is quite simple that we can do that partial v of theta upon partial of theta would be equal to minus partial upon partial r, and instead of rbr I would write 2r square, 2r, because I am multiplying it r with this thing, 2r square plus 3r cube, 3r cube sine of theta. Right. So let's do its derivation. So that would be equal to, I think that would be equal to, it would be equal to minus 4r minus 4r plus 9r cube, 9r square sine of theta. Right. So now we need to calculate v of theta from here. So it means that we need to integrate both sides. So it would be partial
Sir,
v theta. Okay, it should be minus. Okay, that's good. I have realized that I should have written minus here, so it should be minus. Thank you for the correction. So minus partial, it would be equal to minus, I should have written like this, 4r plus 9r sine of theta d of theta. Right. We have got this. So now if we do the integration on both sides, so because we are doing indefinite integration, so it means that there would be some constant of integration, but here it would be, because we are doing partial integration, so it would be a function of radius here rather than a c value, because this is a partial integration. So v of theta would be equal to, if we try to write it, that would be equal to minus 4r theta minus 9r square cos of theta plus function of r, rather than a constant value, because we know that if we perform indefinite integration, then there would be some constant of when we are talking about total differential d terms, in terms of here it should be partial theta, not partial theta here. So because we are performing it the partial integration, so that's why we have got that function of radius here. So if we put this value in the Governing equation, it should give us it should be 0. So it should be equal to 0 dash. And you can always double check it. Right. So any problem in this? Anything which you couldn't understand? Okay. So it seems that everyone is happy. We have done up to now. So now another numerical problem for the stream functions in the polar cylindrical coordinates. So now the streamline in a certain incompressible two-dimensional flow field are all concentric circles. So it means that they are concentric circles so that V of r is equal to 0. So determine the stream function for V of theta. First case V of theta when that is equal to A of r. So first of all, we need to know that what are the relation for the this velocity in terms of stream function uh, in the polar cylindrical coordinates. So if we go back here, so these are the relations. So let me again, okay, I got this. So these are the relations. I copy them and then I paste them here. Oh, sorry. These are the relations. So we can write it. So now in the question we have been given the value of V of theta. V of theta is equal to A of r and V of r is equal to 0. So we need to find the stream function now. So from here, if we V of r is equal to, we write it is I think V of r is equal to A of r and V of theta. Sorry, I think it is V of theta, not V of r. So V of theta and V of r is equal to 0. So first of all, if we put V of r is equal to 0 in the equation of 1 upon r partial psi upon partial r, so we can see that partial psi upon partial r would be equal to 0, and if we do the integration, we can see that that psi function should be a function of I think I am sorry for that. It should be partial theta here, not partial r. Just a minute. Okay, here it should be partial theta. Partial theta. And psi should be, because we are taking the partial integration with respect to partial theta, so it should be function of r. Psi should be function of r, but it didn't give us much information about the exact expression of for the stream function. For that we need to use this relation, which is V of theta, which is equal to minus partial psi upon partial r. So if we do that, so V of theta, which is equal to A of r, so A of r would be equal to minus partial psi upon partial r, and from here uh, partial of psi would be equal to minus A of r into partial r. So if we take the integral on both sides, a is a constant value, so a would come out of integration. So let me put that integration here. So now minus, so we can see that psi would be equal to minus ar squared upon 2. Now here, because we are taking in the integral with respect to function of radius, so it should ideally it should be f of theta here, but because here we have learned that it should be function of radius, so we can just say that it is a constant value, because it cannot be the stream function cannot be function of theta, because v of r that is equal to 0. So partial psi upon partial theta that is equal to 0. So it is not a function of theta. So it means that we can just put c value here, right? So psi is minus a r square upon 2 plus c. So this is the stream function for the first case, and then we do it for a upon r. So it is just the matter of doing that integration again. So for a upon r, if we do the integration again here, so this was the first one. So for the second part, we can just say that partial psi would be equal to minus a partial r upon r. Rather than r into partial r, it is partial r divided by r. So it would be equal to psi would be equal to minus a natural log of r plus c. So in the second case, we have got stream function which is kind of a logarithmic function of radius. So these were the numerical example for the determination of stream function in the cylindrical polar coordinates. Anything which is not clear here? Any query? Everything is good. Now we move on to our next topic, which is conservation of momentum. So now we are going to talk about conservation of momentum. Up till now, we have discussed about conservation of mass, and once we applied it on a differential control volume, we came up with the derivation of continuity equation, and one of the implication of continuity equation is the definition of stream function in two-dimensional steady flow, incompressible flow. So now we are going to extend that differential analysis to the conservation of momentum equation, because we want to know about the relation of velocity with the pressure. So and also the frictional force, which is viscosity. So it means that we need to do that differential analysis and apply that Newton's second law, which is F is equal to ma. So first of all, what is rate of change of momentum for a system? Rate of change of momentum for a system, that would be equal to your FSC knowledge.
Applied force.
Applied force. या net force भी कह सकते हैं. Applied force, yes, that's fine. So we can write that F, क्योंकि जो फोर्स है उसमें रेजिस्टिव फोर्स भी हो सकती है, एंड एज यू हैव मेंशन्ड दैट इट कैन बी अप्लाइड फोर्स, क्योंकि अप्लाइड फोर्स होगी देन देयर वुड बी सम काइंड ऑफ रेजिस्टेंस एज वेल व्हेन there would be a flow against some solid surface. So we can say that rate of change of momentum, that is equal to dP upon dt for a system. Right. Here P is the momentum. P is the momentum. So linear momentum. We are talking about linear momentum. So we know from our FSC knowledge that momentum is the product of velocity and mass. So we can just write it. P is equal to E is equal to, for the system we can write that is velocity vector into that mass of the system. Now if we want to apply it to the this relation of, if we put it here, it would be V into dm. So this is for the whole system. But if we want to talk about differential control volume, in which for the differential control volume, so we are going to talk about differential control volume, for which we have got, just a minute, we have got for the differential control volume, we have got the mass which is equal to delta m, and delta m, if we want to write it, we can write it delta m in terms of density and volume, that is rho into delta v. V is the differential control volume for that particular uh, this series. So now if we talk about differential force which is acting on that differential control volume, we can write del F, that would be equal to d into differential mass into velocity divided by dt. Right. So now then we can do the differentiation by part, and we can write del m into d. V is the velocity vector. Please remember that is the velocity vector divided by dt. And the second term would be equal to v d into delta m by dt. Now, because we are talking about conservation of mass, so we know that for the total mass for the steady flow, it would be equal to 0. So, because the total mass of the system is conserved, so we can say that this term would be equal to 0. So we can just write the differential force on a differential control volume, that would be equal to del F would be equal to del M into dV by dt, and that would be equal to del M into acceleration vector. So for the acceleration vector in the kinematics in chapter number, I think it was chapter number 4, where we discussed about the total derivative. So we know that there would be 3 components of the acceleration vector, and we can write those in the component form. So we would come to that later. First of all, on a differential control volume, we would be talking about the forces which are acting on the differential control volume. So if we talk about the forces, how many forces would be there? There would be, okay, just a minute, I have got visitors, so I would be back maybe in 30 seconds. Just give me 30 seconds. Okay, sorry for the interruption. There was some official task. So now we were talking about the forces which can be acting on a differential control volume. So if we talk about the forces, there can be typically two types of forces. One is volumetric force, and the second one is uh, surface force. So when we talk about volumetric force which acts on a volume, so the first force which comes to mind, that is the body force. So for the body force we can just write the first type of force, that is body force, and that is represented with delta FB. So we know that for the body force, that is delta M into G, and we have got three components in that. In ideal, because we have got for our case, that is only Gy. We usually take that the body force due to the weight. So uh, in the component form, we can say that delta F Bx would be equal to delta M Gx, and then delta F By would be equal to delta M into Gy, and then delta F Bz would be equal to delta M Gz. And we know that this is Gy, that is the main interesting force for this. This component is the fourth component which we discuss, which we usually consider during our fluid mechanics motion. Okay, so this is the body force. The second type of force, which is the surface force. Surface force, and that force act on a particular surface of the element, and it produces some stresses. So we represent it with delta Fs, right? And if we have been given an area, let me draw that here maybe. So how many forces are required here to define the surface forces? We know from our statics knowledge that one should be normal force, which is called delta Fn, and then we have got two shear forces on this surface. So we can define it like first of all we can say that one would be along this direction. We call it delta F1. So one can be x, y, z, and similarly the other one would be delta F2, which is the other direction. If we are talking about that this unit normal outward, it is that direction. So maybe it would be F1 would be x and 2 would be y direction. Right. So if we want to calculate the normal stress for on this surface, so normal stress would be equal to, that would be equal to sigma n, and that would be limit delta A goes to 0. Delta A is basically the this is delta A, which is in this case would be this length into this height. So this is delta A. So delta n at the point it would be equal to delta Fn divided by delta A. And similarly, if we want to calculate shear stress, tau 1 would be equal to limit delta A goes to 0 and delta F1 upon delta A, and similarly tau 2, that is limit delta A goes to 0 delta F2 upon delta A. Right. Now, because if we even consider cubic element, which is the simplest one we can take in Cartesian coordinates. So, how many faces in a cubic differential element. Can anyone tell me? If we have got a cubic element, how many faces are there?
6.
6. Excellent. So we have got 6 faces. So it means that we need to come up with a method of representing that. First of all, we need to know that a particular stress component, it is acting in which direction, and secondly, what is the surface on which it is acting, because there are two things now. So let me draw that cubic element for the moment, and then we can talk a little bit further. Right. So now we can see there are 6 faces. So it means that if we are talking about, and if I say that this is x direction, this is y direction, and out of the board is z direction. So these are the positive x, y, z direction. So if I am talking about the right hand side face, so how to distinguish stress which is acting on the right hand side face from the stress component which is acting on the this top face. So it means that somehow we need to provide the information about the plane on which it is acting and the direction of the stress. Let's for example, if we consider here the normal component, it would be something like delta. Sorry, it would be sigma. Now we will use two subscripts to represent this test. One is first and then second. Now these two are totally different. This second subscript means it tells about direction of stress, and this this first component, it tells us that what is the direction of unit normal out of the plane on which stress is acting. Right? So I hope that you understand this thing, that the first subscript represents the unit normal direction out of the plane on which stress is acting, and the second subscript tells us about the direction of stress. Now let's apply it to the shear stress. So if I am talking about shear stress component in the z direction on this plane, so I would draw it like this, right? So, and because it is a shear stress component, it would be something tau, right? So the first component here, it would be equal to, the first component would be the direction of unit normal. So what it would be? Can anyone tell me? That would be the unit indicator direction of. So what it would be? It would be x. It would be again x, and then the second component would be
XZ over
x0. Excellent. So now it tells us that the shear stress is acting on the right hand side surface, and the direction of shear stress is out of the board, right? And similarly, we can also get another shear stress component which is going in the upward direction. So for this it would be tau tau x y, tau x y. Yes. So I hope that this point is clear. So let me take you through the lecture slide which I have explained up to now, and then we can have a 5-minute break. Maybe it would take a couple of minutes. So we talked about conservation of linear momentum, and I talked about the differential force, which is equal to, comes out to be equal to delta x is equal to delta m into acceleration. And then we talked about the type of forces which can be acting on a controlled volume. So there are basically two types of forces. One is body force, which is usually in our case we take it the weight of the fluid which is passing through that controlled volume. So that would be delta m dy. And that and then second force is the surface force. So as I mentioned that we need one normal force component and two shear components to define surface force on a plane. So that we defined, and then how to calculate how to denote the stresses. I told that we use two subscripts. One, the first subscript shows the direction of the normal to the plane, and the second subscript indicates the direction of the stress. So as it is shown here, sigma x-axis. Here the first subscript is showing the unit normal outward, and then second component is showing the direction of the stress, and you can easily see tau x y and tau x v here. And then okay, so we have mentioned about how to represent a stress by using indexes, not indexes but the subscript. So now what stress should be, how to say that one stress component is a positive. So for that we have got two options. One is that a stress component is positive when it acts in the positive x direction, and the surface normal on which it acts has got outward normal in the positive coordinate direction. Like this here, if you see that it is acting in the positive x direction, and the unit normal, it is also acting in the in the in the positive x. Similarly, if you see here, and then the second option is if it acts in the normal coordinate direction and the unit surface on which it acts has got outward normal in the negative x. So that's why we usually take that normal stress component which is going out, that is taking as positive stress component, and pressure which acts like a compressive force, that is always taken as negative stress, because in that case it is if it is pressure is acting here, so the direction of pressure would be in the negative x, and the unit normal is in the positive x. If we talk about the right hand side phase, and if we talk about the left hand side phase, the pressure direction is positive x, but the unit normal is going outward. So that's why the stress which is produced by the pressure, that is always negative quantity. So similarly for the shear stress, we can see that this tau xy component, it is acting in the positive y direction, and the unit normal, that is also in the positive x. So that's why this direction of tau xy is positive. But if we take it as downward, then it would be negative. So I hope that this point is clear. We can take a break for 5 minutes, and then we can be back at 3:55. Okay, thank you. So it would be the same thing with minus sign. Okay. Now I was talking about tau yx. So on which plane tau yx would sigma xx plus partial by partial y tau yx plus this, right? And similarly, we can also find the values in the